Welcome to the next video in the series on interest rate risk and bond pricing. This one's going to be fully devoted to Macaulay duration, although we will also be touching on modified duration, which in fact is the subject of the next video, but the two are extremely related. Okay, in the previous video, which I hope you watched, we had an opportunity to already define Macaulay duration in what was a rather extreme example, in the sense of the bond being quite extreme. It was a bond with a coupon of as much as 64% of par value, and we're actually going to go back to that bond in just a moment. So let me just recall what I said in the previous recording. Macaulay duration can be thought of from a practical application point of view, that it is the bond holding period or the investment horizon which allows the investor to achieve a balance which balances two elements of interest rate risk, that is reinvestment risk and price risk. And if you watched that previous video, you will have seen that there was a 2-year investment horizon where capital gains and losses were perfectly offsetting reinvestment risk or reinvestment gains or losses. That was kind of the sweet spot, holding the bond, selling the bond after a 2-year period, which was 1 year short of its full term to maturity. Now, that is the definition, or that is the kind of the application. How do you actually compute Macaulay duration? Okay, so this is what we're going to be doing in this lesson. To compute Macaulay duration, you have to take into account the fact that it is actually the weighted average of the time to receipt, of the bond's cash flows, one by one. Now, we're going to do this computation kind of on paper, and then we'll use the calculator to do it again in a shorter way. But I need you to understand the logic so that you can later just breeze over this and use the calculator, knowing fully well how this is really done, kind of what goes on inside your calculator. So I'm going to base everything on the previous example. In the previous video, the example was such that we had a 3-year bond which had a 100 par value and a very extreme 64% coupon. Okay, and you may recall that we initially assumed that it had a 60% yield to maturity, right? Now, if you can't remember this, it may be a good idea to go back to the previous video. If you can just about remember, then fine. And you may also remember that the Macaulay duration for this bond was 2 years. I know it, because that was the holding period for which we achieved the balance between reinvestment risk and price risk. But I forced that 2 years on you in the previous video. Now I'll show you how I got it. I did a computation which involved computing the weighted average of time to receipt. And let me show you how it is done. Your curriculum outlines a sort of very methodical approach to it. So you're supposed to construct a table. In the exam you won't really do this because you'll do this in the calculator, but your book talks about this all the time, so I'll show you. I'm going to assume, and like I did before, that these coupons are paid annually. So you're going to have 1, 2, 3 coupon payment periods. Now, at the date of issue, the time to receipt, the time until you receive these coupons is accordingly 1 year, 2 years and 3 years, or it's better to think in terms of periods, because later on we'll think about a bond that pays coupons semi-annually. Now, to be honest, these two columns are going to be equal for all the computations that you do at the issuance date of a bond's issue, or if you do a computation done at a coupon date, just after a coupon has been paid, and you have a full sort of interest period until the next coupon is received. Time to receive, think of this in terms of periods. It's better than to assume that this is always going to be years. However, if you came across a bond for which the settlement date is somewhere in between coupon payments, so it has some accrued interest, etc., etc., then the two are not equal. Now, your book contains examples of these computations. They're extremely difficult to do by hand. You'll always use your calculator to do such computations because your calculator is able to do this. Okay, now I'm going to draw the next column, and I'm going to say cash flow. What's the cash flow which will come to the investor holding the bond at these individual moments, in these individual periods? Well, a coupon of 64 over here, another coupon of 64 over here, and finally 164 including the par value of the bond, right? The face value of the bond. Now, let's do the PV computation, the present value. For this, I'll need the calculator. Look, we've got a YTM of 60% here, so I'm going to discount each of these values, starting with the 64, by dividing by 1 plus the YTM raised to the relevant power. For the first period, it's just 1. So I'm dividing 64 by 1.6. That equals a nice round 40. The next cash flow, another 64, divided by 1.6, but raised to the power of 2. Only 25. And of course, this final cash flow, 164, needs to be divided by a factor of 1.6 raised to the power of 3, so y to the power of x followed by 3, and that gives approximately 40.04. Nice. Now I need to sum up all these cash flows, so I've got 40 plus 25 plus 40.04, which gives a sum of 105.04, and that's going to be the bond price. In fact, it was the bond price that we computed in the previous video. Okay, what comes next? Very important, the weight factors. The way I will compute weights is by taking the PV of each cash flow, and for the first one it's 40, and dividing by the overall sum of these present values. So 40 divided by 105.04, 38, I guess 0.1%, 0.381. In other words, the first cash flow has a weight of 38.1% in the overall bond price. The bond price is just the sum of all the PVs of the individual cash flows, and the weight of the first one is 38.1. For the second, I repeat the same thing. I take 25 divided by 105.04, and I get, well, 0.238, and the final one, 40.03 divided by 105.04. Okay, it's just like the first one, isn't it? 0.381. And this spread of the weights is perfectly in line with the fact that we're going to get a Macaulay duration of 2. You'll see in a moment. So, if I just technically, there's no need to really do this, sum up all these weights, I should get a result of 0.381 twice at the top and at the bottom, plus 0.238, as you can see, it gives 1. All the weights sum up to 1, so 100%. And now the most important bit, You take the column labeled time to receipt and you multiply the value sitting there by the relevant weight. So for the first one, it would be 1 times 0.381, which obviously gives 0.381. But for the second, you take this 2 and multiply by 0.238. 0.238 times 2 gives 0.476. Okay. And for the third one, 3 times 0.381. That's 1.143, and now we sum all of these times to receipt times weight. So this plus this plus this, 3 numbers. I've got the final one on my calculator, so plus 0.476 plus 0.381 equals, voila, it equals 2. And that is our bond's Macaulay duration, which we kind of knew from the previous video that it would be 2. Okay. Good. Now, this is the long way to do this computation. In the exam, you have to be, well, you can do this, but it may be helpful to do this a lot quicker. If you're given a scenario like a 3-year bond with a coupon, it won't be as extreme as 64 here and the yield to maturity, right? Please utilize the bond worksheet. So press second followed by bond, which is how you access the bond worksheet. Okay, second followed by, well, bond is the secondary function of the key labeled 9, the digit 9. So you've got bond at the top and you're in the worksheet. Now, I've cleared the worksheet, but it doesn't clear the dates necessarily. So I've got some dates sitting in there from sort of previous calculations. And what you see already here is that my settlement date, SDT, is January the 1st, 2024. This is the sort of American convention for quoting dates. To input your own date, but make it, I suggest make it the 1st of January 2024. I'm recording this video in 2024, not necessarily January, but 2024. So this is why I made it 1st of January 2024. To be honest, you could make it anything. You could do 1st of July 2024. Why not? I mean, let's do something different. If I wanted to do July 2024, I would do 7 followed by the dot, the decimal point. Then give your calculator the day 01 and the year, but only the last 2 digits, 24, and then press the enter key. Now it says July the 1st, 2024. That's when we get into the investment. Okay, press the down arrow and it asks you for the coupon. Well, give the calculator the coupon. Irrespective of the frequency of coupon payments, give the calculator the full annual coupon. So for CPN, please input 64 followed by enter. 64, enter, good. Press the down arrow again, and now it's asking you for the redemption date, the RDT, the redemption date. We're told in this example that, or I'm telling you that this is a 3-year bond, so simply add 3 years to whatever you input as your settlement date. I made this date up, so just keep it consistent. July the 1st and add 3 years, make it 27. Or if you started with a different settlement date, just add 3 years to it. 7.0127. And of course, follow up with the enter key. Nice. Okay, if you press the down arrow again, you'll see RV. which is an assumed 100. If you don't see RV 100, just input 100 always follow up by enter. Okay, then it asks you for the convention it should use. It will really not matter, whether it's counting actual number of days or assuming 360 days in the year. It will only matter if you're doing something, computation in between coupon payments, where that convention is important. You can change the convention by pressing second followed by set. I'll go back to actual, which is the default. How many coupons are being paid per year? Well, in my case, I'm assuming annual coupon payments, so I'm going to actually press second followed by the enter key, which has set above it, and I know set is the relevant one to use now because my calculator is showing that at the top of display. If you want to change it, go to the set function, which is the secondary function of enter. Okay, and I've got 1 over y now, which is what I want, once per year. And now it says give me the yield, where for the yield I want to enter 60% of the yield to maturity. So 60, of course, followed by enter. And you may think, well, this is an awful lot of stuff that you need to input. Kind of, but it's, I'm talking and I'm doing this, so it's taking a lot longer than it would. Once you've practiced a bit, you'll see that it works really well. And look, when you press the down arrow again, it says, oh, price, but at the top it says I'm ready to compute. So compute the price, press the CPT key, and out pops a price equal to 100, and so we press the compute key, 105.039 or 04, which is exactly the price I derived over here. So that's a good sign. Because I'm assuming everything is happening on the coupon payment date, we've got no accrued interest, and then you see the parameter duration displaying 1.25, which is absolutely not what we got. We got a Macaulay duration of 2, and you may be thinking, well, he's made a mistake or something. Well, no. What your calculator displays is something that's also extremely important. It displays modified duration, which we'll be talking about in the next couple of videos, in the future. But modified duration is a measure of sensitivity to interest rate changes of the bond price. However, there is a nice way in which you can convert between Macaulay duration and modified duration. What you've got to know at this point is that modified duration, so mod dur, equals Macaulay duration divided by 1 plus r, where r is the yield per coupon period. And because in this case we had annual coupons being paid annually and 60% was our YTM, well, R equals 60. So let's do a quick conversion between the two. Macaulay duration will equal whatever modified duration was, 125, as displayed on our calculator, times 1.6. Let's see if this works. I've still got the 1.25. If I multiply that by 1.6, oh, very nice, I get 2. Now this is measured in right now in years. It's our sort of annualized Macaulay duration. Later on we'll be talking about how this can be, how this is not always expressed in years, but for now it is expressed in years, and it's exactly the same as we had in the previous video where I showed you that this is the investment period or the holding period, which balances reinvestment risk and price risk. It's an important result. Okay, now, what if this bond had the same parameters? So same bond as above, but with semi-annual coupons. Okay, and once again, I want to show you the full computation as it is done in your book with a table, and then do the same thing on the calculator, right, which will be much easier and much quicker, especially as we've got many of the inputs in already, most of them. We just need to change the assumption of 1 coupon per year to 2 coupons per year. But I want to show you the full working, at least once. So now we're not going to have 3 periods. It's a 3-year bond, but it has 1, 2, 3, 4, 5, 6 dates on which cash flows are paid. And of course, the time to receipt, because we are analyzing the, or I'm assuming that we're analyzing this, measuring this Macaulay duration at the time of the bond's issue. You have the same numbers here. As I previously mentioned, the only time you'd have a difference is if you were buying the bond in between coupon payment dates. So for period number 1, you may have less than a full period, less than a full, semi-annual period, in which case this would be 0 point something. This is measured in periods. So if the relevant period is 6 months, then 1 period means 6 months. Less than 1 means something less than 6 months. Okay, what would be the relevant cash flows? Well, we're still assuming that the bond pays that rather large coupon of 64. However, now it's going to be split into 2 halves over the course of the year. So you'll get, after the first 6 months, 32, another 32, another 32, and so forth and so on. And at the end of the bond's life, 132. Good. What would be the present value of each of these cash flows? As you can see, this is now getting ridiculously difficult, and I'm only going to do this with you once and then tell you for everything in the future, just use the bond worksheet, to be honest. However, the next video where I compute modified duration, because that's an older video which I showed before, I still use the long method there, but you can easily go and try and do it with the bond worksheet. It will work, don't worry. So how do I get this PV? Well, I'll take the 32 and I'll discount it. So 32 discounted, but because it's being discounted over a 6-month period, due to the semi-annual coupon nature of these cash flows, semi-annual nature of these coupon cash flows, sorry, I'm going to discount this by dividing by 1.3. So half of the annualized YTM using the bond equivalent yield convention. So 32 divided by 1.3, okay, 32 divided by 1.3 gives 24.615. Now I'm trying to be as precise here as is sort of realistically feasible. I could go and do more decimal places, but I can't be bothered. I think 3 decimal places is going to be fine. Now the next one is again 32, but this time divided by 1.3 to the power of 2, 18.935. Let's just note this down. Next one, 32 divided by, right, I won't be writing everything down now, 1.3 to the power of 3, 14.565. 32 divided by 1.3 to the power of 4. That's where the time to receipt or the period come in handy. Labeling them properly, 11.204. Then 32 divided by 1.3 to the power of 5, 8.619. And finally 132 divided by 1.3 raised to the power of 6, 27.347. Let's see what happens when we add all of these PVs in this column. So 24.615 plus 18.935 plus 14.565 plus 11.204 plus 8.619. You really don't want to do this the long way. I'm just trying to prove to you that we'll get the same result on the calculator. Of course you could trust me, but I want you to be confident how this is done. 105.285, that's the total, and this will be the bond price. It's slightly different to the price we had before when we were assuming annual coupons, very similar, but nevertheless slightly different. Now, those all important weights. The weights come from checking what portion each PV is of the overall bond value, of the overall price. As you can see, the first coupon, its present value makes up for a big portion of the weight. So 24.615 divided by that 105.285, 0.234, that's our first weight. Then for the second, 18.935, divide that by 105.285, that's only 0.180. Next one, 14.565, divide that by 105.285, 0.138, 11.204 divided by 105.285, 0.106, 8.619 divided by 105.285, 0.082, one to go, the big one, 27.347 divided by 105.285, okay, 0.260. Right, these are the weights. And you may recall from the computation we did just a moment ago that the last step is to take each of these weights and multiply by the relevant time to receipt, or time to receipt multiplied by weight. It really doesn't matter. So take this number, 1, multiply by the weight we just calculated, and then add all of them up. I'll add all of them up, 0.234. Now, I really don't want to spend too much time. Well, I've already spent a lot of time here, but maybe we can just try to do this on the calculator without writing the results down. So I know the first result of the multiplication is 0.234. Because I've got my calculator set up under algebraic operating system, it should respect the basic laws of algebra, so do multiplication before addition. So let's just add 2 times 0.18, basically this number times this number, add again 3 times 0.138, add 4 times 0.106, add 5 times 0.082, and add 6 times 0.26. Unless I've made a blunder, I don't think so, we get a total down here of 3.402. So, you know, I do all of these multiplications, all of them, and I didn't really care about the intermediate results. I just wanted the total. That's the good one I wanted. Okay. This is Macaulay duration, but please appreciate that even though we had what in essence was a 3-year bond, it was supposed to be a 3-year bond, we got a result which is more than 3, didn't we? Which is weird. You can't get a result which is more than 3 for a 3-year bond. It's the weighted average of the time weighted average of those times to receipt. But we got a result which is more than 3, because this is not expressed in years. This is expressed in semi-annual periods, 3.4 semi-annual periods, and you've got to be very careful about drawing conclusions here. In order to produce what we call annualized Macaulay duration, you just need to divide this by 2. And, if you do, you get a result which is more or less 1.7, don't you? 1.7. And this is going to be your annualized Macaulay duration, which is pretty much what you'll always be asked about. Nobody, quotes duration in any other way than annualized. Okay. Now, let's see whether we can get the same result on the calculator. Let's have a go. I'm going to once again enter the bond worksheet, where I've got my previous data, the settlement date, the coupon being 64, the redemption date being 3 years later, I guess, redemption value, that's called actual convention. That's good. Now, the thing I need to switch is the assumption of the coupon being paid not once a year, like here, but twice a year. So I do this by pressing second followed by enter, which has set as its secondary function. The yield is still 60. It's the annual yield of 60, and your calculator will know how to handle stuff, semi-annually. And I'm pressing the down arrow again, and let's see what's happened. Well, it's saying I'm ready to compute, so press the compute button, and you can see it's got a fresh price, 105,285, which is very much in line with the price we computed over here. That's a very good sign. No accrued interest. Let's check for the duration. Well, it says duration on the calculator 1.308. Okay. We know that this is modified duration, 1.308, and your calculator will always display annualized modified duration, right? It's always annualized. Now, I told you before how to convert between Macaulay and modified. Modified duration is always equal to Mac duration divided by 1 plus R. But I also mentioned that the R has to be always expressed on a per period basis. So even though the Macaulay duration, the modified duration displayed over here is annualized, when you make the relevant conversion, you still have to use not 60%, the full YTM, but half of it, so 30% per period in this example, in this rather extreme example. So Mac duration would be what your calculator displays, 1.308 multiplied by 1 plus half of 60%. So just a factor of 1.3. Let's see if that works. This multiplied by 1.3 gives 1.7, which is what we wanted, what we computed the long way. So look, use your calculator always to compute duration. Your calculator will return modified duration. If you're asked for Macaulay duration, you need to multiply by 1 plus R, but with annual coupon paying bonds, the R will simply be the yield to maturity on the bond expressed in an annualized way, 60%. This is why over here we multiplied by 1.6 in the first version of the example where we had an annual coupon paying bond. In the case of a semi-annual coupon paying bond, you also multiply by 1 plus R, but scale it down to a per coupon period basis, which in this case would be divided by 60% by 2, so you get 1.3, and you will arrive at the right result, and this will save you so much time in the exam, providing your calculator can perform these computations. Now, this is also brilliant if ever you are asked, although I don't think it would be fair to ask you to do this in the exam, if you are asked in the exam to perform a duration computation using a bond price, a bond that is somewhere in between its coupon dates, because on this worksheet you can input a settlement date which is anywhere, and your calculator will appreciate that if you've entered a redemption date like here, the 1st of July, and your settlement date isn't the 1st of July, or maybe 6 months later, or before the 1st of July, it will draw the right conclusions and say, oh, this is somewhere in between coupon payment dates. I don't think it's fair to ask you to do that in the exam. It's a bit too much work, but still, your calculator can cope with it.